Human gait involves a complex interaction of skeletal, neurological, and muscular systems. A thorough understanding of the principles of normal gait is the bedrock on which all treatment of gait pathology must be based. Yet, in our preparation to become therapists, physicians, or surgeons, we spend a lot of time on anatomy, but very little time on the physiology and mechanics of locomotion. Consequently, before we can start to discuss any condition that impairs gait, we need to spend some time learning about normal gait, including its development, description, physiology, and how it is assessed. Quadrupeds usually stand and walk shortly after birth. That is not the case with bipeds. At least part of the reason for this difference lies in the location of the body's center of mass. In quadrupeds, the center of mass is located within the base of support, making them inherently stable. In humans, on the other hand, our center of mass typically lies just in front of the S2 vertebra. Thus, we are inherently unstable, much like an inverted pendulum. Therefore, even with quiet standing, we must continually make postural adjustments to maintain our center of mass within our base of support. Since quadrupedal gait is inherently more stable, infants begin the process of ambulation in a quadrupedal fashion, by crawling. Typically, infants start to crawl at about 6 months. Stability while standing is the next major motor milestone that has to be mastered. Infants usually pull up to stand while holding onto a table or other object at about 8 to 10 months of age, and independent walking starts a few months later. However, walking skills continue to evolve for many years. The risk aversion hypothesis states that as the central nervous system matures, the child becomes more confident and therefore willing to take more risks. Consequently, as balance improves, the walking base decreases, reciprocal arm swing develops, and cadence decreases, while at the same time step length, walking velocity, and single limb stance time all increase. After the age of 4, a child's gait looks very much like that of an adult. The problem is that as the child matures, central nervous system development and musculoskeletal growth progress in tandem, making it difficult to discern changes due to growth from those due to neurological maturation. This problem has largely been solved by scaling gait parameters such as speed, step length, and cadence to stature. This scaling has led to the conclusion that gait is largely mature after about 80 months of age. Therefore, we could conclude that gait is mature by around 6.5 years. Neurologically, the initiation of gait starts in an area of the brain known as the supplementary motor cortex, just anterior to the motor strip. The motor system is hierarchical and is made up of a chain of command which extends from the cortical centers down to the nerves that innervate the muscles. The components of the system include the cortical motor control centers, the centers from which all motor activity begins. The basal ganglia, which functions much like the disk drive of a computer, since it contains a database of previous learned activities. The cerebellum, which monitors the movement being performed and reports errors back to the cortical centers. The brainstem motor nuclei, which control the background of posture and tone against which voluntary movements can be performed. And finally, the central pattern generators in the spinal cord, which generate a consistent and specific movement pattern when stimulated. The impulse to start walking comes from the supplementary motor cortex. It begins the action by accessing the basal ganglia for information as to how the specific activity will be performed. The basal ganglia is an area of the brain where motor memories are stored, and using a computer analogy, it can be thought of as the brain's disk drive. Once the supplementary motor cortex receives instructions as to how to carry out the movement from the basal ganglia, the set of instructions is divided. One copy moves through the other 3 pyramidal areas of motor control, and from there down through the control pyramid. Simultaneously, a second copy of the instruction goes to the cerebellum, which monitors the activity that is to be carried out and reports any errors back to the cortex so they can be corrected. The outputs of the cortical neurons responsible for the movement itself are of 2 types. 1, pyramidal, which constitute about 10% of the total, and 2, extrapyramidal, which make up the other 90%. The pyramidal fibers can be thought of as the express buses. They pass uninterrupted through the pyramids in the midbrain and descend all the way down to the motor neurons in the spinal cord. They are responsible for the fine, coordinated motions of the hands and feet that are needed to carry out the activity. The extrapyramidal fibers, on the other hand, end in the vestibular and reticular nuclei in the midbrain. These nuclei, in turn, are distributed to central pattern generators in the spinal cord, which control balance and posture throughout the activity, as well as the coordinated movements of the legs and/or arms that are necessary for that particular movement pattern to occur. The central pattern generators in the spinal cord can be thought of as analogous to piano keys. On a piano, when a particular key is struck, it will always produce the same note. In the same way, every time a central pattern generator is stimulated, it will always produce the same movement pattern. It all seems so effortless, but the neurological and musculoskeletal systems interact in an extremely complex process.